V, close our eyes and select a J. And do site-specific recombination. So we're going to take randomly the end of any one of the V's and the beginning of any one of the J's and literally do site-specific recombination. Remember, Lambda used that term for integration into E. coli, site-specific recombination. It's not using the general recombination system. It's using a very special recombination system, special for this system and one other one. And so we're going to go from the germline sequence. Oh, and so everything in between, all that DNA is going to be thrown away. Big chunk of DNA. But it's only in this cell and all of its daughters. And so this is going to give us L2, B2, promoter, J4, J5, J6, and so now we have antibody gene, a light chain antibody gene. Notice there's a gene that actually looks kind of like globin. So it's a gene with 3 exons. The first exon is the leader. The second exon is the VJ exon. The third exon is the haploconstant region. We now have a real, complete gene made from 2 distal segments, 2 cassettes that we put together by recombination. We have a promoter, a gene regulator. It's in the intron, but it doesn't matter, and a transcription terminator. And so now this gene can be activated and fired up. And we can start transcribing it and make an antibody. And the same thing is going to happen, but in a more complex way. Look in your book and find the details for the heavy chain. Heavy chain is probably 3 or 4 times more complex. But the basic mechanisms are exactly the same. Yes? Oh, J stands for joining. Thank you. I should have mentioned that. The J stands, those are the joining segments. That's when the V joins to the C, but it doesn't really join the C. It joins to a J region. And so this is the gene structure that you find in your circulating B cells, that population, that small proportion of white blood cells circulating along with the red blood cells.
How come, like, J5 and 6 got to stay along, but everything from B2 to 200?
So the thing was that everything from there to there we eliminated. Now J5 and J6, you see, are in what we now call an intron between the VJ exon and the C exon, but they're just sequences that didn't get used. They're in the intron, and when this message gets transcribed and spliced, it just gets thrown away. There was nothing else to do with them. Whatever is in between gets eliminated. If we had used J1 and we had a larger intron with 2, 3, 4, 5, and 6 J's in the bigger intron, but it would still get spliced out so it doesn't affect the final product.
What is the gene label between the promoter and B2?
I didn't get that.
The gene, like what is it labeled between the promoter and the alpha?
So we have L2, V2, J4, and then C kappa. Is that what you're asking?
Yeah, I was asking for that.
Okay.
Yeah, thanks.
Why is L1 and P1 not on there? Okay.
I just elected not to.
But it doesn't use it?
No, that's right, it doesn't use it, because this enhancer is going to control the nearest promoter. And so you're right, I mean, it is definitely out there, but it's non-functional. Anybody else? So we are getting close to the answer to the big question, how do you make tens of millions of different antibody proteins from a few hundred? You've got about 100 or so here, you've got another 100 or so in the lambda, and you've got 100 to 150 in the heavy chain. And from those few hundred, you make millions, tens of millions, uncountable numbers of antibodies.
What is the
Leader. L stands for leader, V stands for variable, J stands for joining, C for constant. Those are the major parts, those are the parts of the kappa light chain gene. Lambda is very, very similar, a little bit different organization. Anybody else? So, immunoglobulin diversity. How do we get tens of millions, even hundreds of millions of proteins from this and lambda and heavy chain? First of all, we have multiple variable regions. Secondly, multiple J's. So those will multiply together. If we have 106, we have 600 different possible combinations.
So the J's like J exon, yes?
Well, so the J, well, no, not really, because when the recombination happens, it gets tacked onto the V, and so it's called the VJ exon. So a J is never a standalone exon. Anybody else? So one way in which we make millions is by multiple V's and multiple J's. Now the second way is if we look closely here, let me bring that down. If we look closely at that left joint of what will become the VJ exon, the reality is we don't just cut it at the end of the box, but the way the system cuts is it can cut there, or there, or there, or there, or there. And so what we have is called imprecise excision. And that happens on both ends. So imprecise excision on both ends means that if you cut, let's use that as the starting point, if you cut there, you have one sequence, that's a sequence in the open reading frame. But if you cut one base before or one base after, that's a real frame shift potential. You're changing the reading frame. That's in essence an insertion or deletion of one base. And so because of that, we have this imprecise excision there, and I'm not going to draw it in, imprecise excision on J4. And so that's going to give us a variable readout of amino acids. The reality is that the blue box is where antigen binds. So the binding is going to be right at that end of V, into all the J, and into the beginning of C. And so, if you can visualize now, we're going to have this tremendous diversity because of imprecise excision. But that's not all. Because the next thing that happens is called nibble add. So I already described the nibble part. Add means that we're going to randomly add nucleotides. So an enzyme is going to come in once the cut is made and the end of this segment of DNA is now open. Let's say we open it there. An enzyme is going to come in and just randomly add a few nucleotides. To both ends. Both ends are being treated exactly the same way. And so again, it's this region that encompasses that red line. The red line is exactly where we made that site-specific recombination. We nibbled out a few bases randomly. Could be one, could be two, could be three. And then we added a few random nucleotides. 1, 2, 3, 4. And every one you're going to get a different protein, a slightly different protein. It's uncountable, the number of proteins that you can make. Because we're not done with why is there diversity yet. So this is just the mechanism of what's going on to make a right chain. Any questions on that? Next, we have multiple combinations of light chains and heavy chains. And so each cell will only make one light chain. So there's potential problem, and you see the problem in this system if you're randomly adding and subtracting nucleotides in an open reading frame.
Might make a stop codon.
Yeah, it might make a stop codon, that's exactly right. And it happens. And if that happens, this is the first thing that goes. If you make a stop codon and make no protein, the cell will automatically switch and do the same thing to lambda. So kappa is the first choice, lambda is the second. If the same thing happens to lambda, the cell will undergo programmed cell death. It's no use. You can't make an antibody, it's all it's good for. The cell will die. If we make either lambda or kappa, now you have to have a good heavy chain. Same thing happens at the heavy chain.
Is producing a stop codon very rare?
I think it's probably pretty common. I think it's probably pretty common. But there's more of a problem in that not only can you make stop codons, you can also make self-antibodies, antibodies against self. And so this whole thing is set up so that you have to make a good antibody. I don't know that we're going to have time to go through the biology. We'll pick that up on Monday. But this whole thing is designed to make an antibody, which then gets filtered out. Because the cell can't afford to make a B cell and throw it out into the circulatory system in case it's made an antibody against you. This is the way the system works. Now, the heavy chain, if you look in your book, we're not going to do it. But if you look in your book, the heavy chain is twice as complex. So the light chain only has one site-specific recombination. The heavy chain has two different site-specific recombinations. Either one can lead to no reaction, a stop codon or self, and get eliminated. This is all happening randomly. Now, the big mutation in this system is the recombination system. It's called RAG. The RAG system. People who have mutations, homozygous mutations, these are the children in the bubble. These are children that can make zero antibodies and have no means of fighting off infections, and they have to be extraordinarily careful. Most die of infections at a fairly young age, just because they can't make antibodies. But this system is designed to give maximum variability. And the variability is right in here due to all of those things. The exact same thing happens in heavy chain, but it just happens twice. Any questions on antibody?
What does RAG stand for?
I was hoping nobody would ask that. I don't remember. Do you guys know what RAG stands for? Nah, I probably think so. Okay. Someone will Google it. So this is the mechanism. Now, the biology of this system is such that this happens every day, every minute of your life. Your red blood cells, the hemoglobin, yeah. Recombination activation gene. Thank you. I knew somebody would Google it. Okay? So it's recombination. This happens every day. And the cells have about a month lifetime. And so every day you are randomly making millions of different antibodies. And every day millions of different B cells are dying. You cannot sit down and think, I'm going to make an influenza antibody tonight. That's not the way the system works. The system makes antibodies randomly, and if one happens to hit an antigen, that's going to be clonally expanded. And so what that looks like so all of the antibodies are sitting out on the cell surface. Remember, each cell is only allowed to make one antibody. It tries kappa first,